Not that kind of sine. For this sine, you'll need the unit circle.
In review, sine of theta is the ratio of the opposite side over the hypotenuse. Because the hypotenuse is the longest side of the triangle, the denominator of this fraction will always be greater than or equal to the numerator, so sine will never be greater than 1. Another way to look at this is on the unit circle. Sine is the y value of the unit circle, and we can see that y is never greater than 1, so sine will never be greater than 1. That is the first key point to remember about sine, that it will never be greater than 1 or less than negative 1. The second point to remember when graphing a sine function is that sine is repetitive. We can continue to go around the unit circle as many times as we want, but once we reach 2 pi, the values of sine just keep repeating. If we are to look at the unit circle, we can pull off of it the main points that will be on our graph. When x is 0, y will also be 0. When x is pi over 2, y will be 1. When x is pi, y will be 0. When x is 3 pi over 2, y will be negative 1. Now we can put these points on a graph. When graphing the sine function, instead of going up by whole numbers on the x-axis, we go up by angles. This is because the angle is the independent variable, and sine is dependent on what the angle is, so it goes on the y-axis, while the angles go on the x-axis. The same points that we had on our table of values can be put on our graph. They are connected in a curved line like so. If you were to choose the sine of any other angle, you would find it on this curve as well. When angles are negative, we go around the unit circle backwards. So at negative pi, we have the same point as pi over 3, negative pi as pi, and so on. Then this can be connected as well to the positive side of the graph. The domain of the graph y equals sine of x is that x is an element of any real number. The range is that y is an element of any real number so long as y is greater than or equal to negative 1 or less than or equal to 1, which can also be written like so. Now let's go over some terminology associated with the graph of the sine function. The amplitude is the height of the graph, or the distance from its center to the tallest point. So in this case, it's 1. The period is the amount of time it takes for the graph to complete one cycle. So for this graph, it is 2 pi. And the cycle is the shape that you see here after going around the unit circle once. If this is the base sine function, what would it look like if it was negative? Pause the video now so that you have some time to sketch down your ideas. Any angle that is negative just means that we go around the unit circle backwards. So, at sine of negative pi over 2 is the same as sine of 3 pi over 2, or negative 1. Sine of negative pi is the same as sine of pi at 0. Sine of negative 3 pi over 2 is the same as sine of pi over 2, which is 1, and then sine of negative 2 pi is 0. To graph this, we can put in the points that we pulled off the unit circle, and then connect them. You can see that the shape it forms is still a sine wave. However, when compared to the base function, y equals sine of x, you can see that they appear to be opposites. While y equals sine of x starts and goes up, y equals negative sine starts and goes down. Now let's look at the transformations that can occur on a sine graph. First, we have y equals sine x plus 1, which is a vertical translation of 1. This means that we add 1 to all of the points on the y equals sine x graph. Instead of the center of the graph being at y equals 0, it will now be at y equals 1. We can fill in all the same points with pi over 2 being at 1, pi being at 0, and so on. We will just use the line y equals 1 as our starting point. If it helps, you can draw on a dotted center line like we have done. Next, we will graph the function y equals sine of x minus pi over 2. This graph shows a phase shift to the right, or a horizontal translation. Now it starts at pi over 2, not 0, and the cycle ends at 5 pi over 2. The idea of the graph shifting more positive may be confusing, as it is net x minus pi over 2. This happens because each x value loses pi over 2 before we find the sine of it. So to get the same value of sine, we must add pi over 2 to the original x, and that shifts it positive. As well, now instead of going through the y-axis at 0, it goes through the y-axis at -1.
For the next part, we are going to go over how to graph a vertical stretch or compression on a sine function. In this example, we will be using the equation y equals 2 sine x. 2, the number in front of the function, represents a vertical stretch, since 2 is a positive number. What this means is that the 2 will now be the new amplitude of the graph. Since sine x is being multiplied by 2, all y values are also multiplied by 2, and the graph is 2 times bigger vertically. Using this information, we are now going to try to graph y equals 2 sine x. As you can see from the graph, instead of the sine wave having an amplitude of 2, the y values go up to 2 and down to -2. The x values, however, remain unchanged. Next, we're going to be using the equation of y equals sine 2x to demonstrate how to graph a horizontal stretch or compression on a sine function. 2, the number in front of this x, represents the number of cycles in 2 pi. In the base sine function of y equals sine x, the number in front of the x is 1, so there's 1 cycle in 2 pi. Since we are using y equals sine 2x, there are 2 cycles in 2 pi. To demonstrate this idea further, we will be using y equals sine 4x. The 4 in front of the x means that there will be 4 cycles in 2 pi. Since pi over 2 is the endpoint for one cycle of the graph, the period is pi over 2. In the red graph of y equals sine 2x, the period is at pi.
The idea of the length of the period, as well as the number in front of the x, can be seen algebraically. The period is equal to 2 pi, which is the whole, over k, which is the number in front of the x that represents the number of cycles in 2 pi. In this case, k is 4, and 2 pi over 4 is equal to pi over 2. If we look at our graph, we can also see that the period is pi over 2. In summary, all of this can be summed up in the equation y equals a sine of k times x minus d plus c. The a value affects the vertical compression or stretch, changing the amplitude of the function. The k values are the number of cycles in 2 pi, which is the horizontal stretches and compressions. C is the vertical shift or translation, which moves the function up or down. Finally, the d values are the horizontal translation, which moves the whole function left or right. Here are 4 practice problems. Pause the video now so you have a chance to try them. Here is the graph for A, which has an amplitude of 3. The graph for B, which now has a period of 4 pi. The graph for C, which was shifted 3 up. And the graph for D, which was shifted negative pi to the left.
Thanks for watching.